It's possible when talking about mechanical systems and electronic circuits to develop analogs between them. So if you remember, across variables, such as velocity and voltage, can be related with through variables, force and current, through various variables. And we have differential equations that allow us to turn cross variables into through variables. So also remember that the dynamical system has a behavior that's described by its equations of motion. So the motion of some mass inside a dynamical system has to obey the differential equation, the ODE that describes it. So that's the equation of motion. So here's an idea. Let's say that we have some equation of motion, and we have it for a dynamical system, well, a mechanical system. So what circuit would have the equivalent equations of motion? So this would be an interesting way to see whether you really understand what the fundamental topics are. But I have to warn you, some of the analogies that are made are not that easy to understand. So you have to go to the math first, and then move from the math to your deep understanding. So let's begin with a couple of atomic examples. So the very first one that I'm going to have is a force that pushes on this mass m1, and we've indicated direction of motion here with x1. So you may remember that we have F as m1 x1 double dot. So force is mass times acceleration here because direction of motion is indicated by x1, direction of acceleration is x1 double dot. So this is an extremely simple example. But clearly if you kept pushing with this force and there was no resistance, eventually the mass would be going really fast, right? And eventually it would, do things that it's not supposed to do. So we can also rewrite this as m1 v1 dot instead of x1 double dot, because v1, of course, is x1 dot. So v1 dot is x1 double dot. So now let's go into the twilight zone. Here we're going to actually talk about circuits using the same kinds of variables. So the first equation that I want to write is I is equal to mass times the rate of change in time of voltage. So I've used force as a through variable, and now I've mapped that to current as a through variable. We began with velocity as an across variable, and now we have voltage as an across variable. So what does this look like as a circuit? Well, we already have a circuit component that obeys the law of I equals something times voltage with respect to time. And that's a capacitor. So if we imagine that the mass acts like a capacitor here, then what we get is that the analogous circuit to this dynamical physical system is just a capacitor mapped in parallel with a current source. So clearly you would never turn on this current source and leave it on with a physical device, right? Eventually that capacitor would explode and you would see a capacitor juice all over the place. So the same thing is true with a mass on the left. If you kept pushing with the same force, you would eventually see something really bad happen. So either the mass will be going so fast it'll start to violate all kinds of laws and you'll get pulled over by the cops, or of course eventually in an ideal world you'd be exceeding the speed of light, which is not allowed either. So this is the very first example. So the mass acts like a capacitance. Let's look at a second example. So now I have a mass and I'm attaching that mass to a spring. So the spring has some constant K1. So let's first talk about what are the ordinary differential equations that map here. So if we have F is the sum of all forces, so here m1 x1 double dot plus k1 x1. So when we push with this force, that's equivalent to the inertial motion in the same direction plus k1 x1. So we can rewrite this as m1 v1 dot plus k1 integral v1 dt. So I've taken x1 and taken its integral so that I can write it as v1. So we can rewrite this as a current source, I, with the capacitor, m1. And what is k1 times the integral of voltage? Well, we already know that voltage is, across an inductor, is L times the derivative of the current. So we can integrate the voltage to get L times I, and divide through by L to get an equation for I in terms of voltage. So now we can see that the spring actually acts like an inductor. So the first current comes out of this node and drives south through M1. The second current also comes out of the same node and drives through the inductor. So here we have the mass acting like a capacitor and the spring acting like an inductor. Let's look at the third case. So now I'm not using a spring, I'm using a damper. So the damper has some physical coefficient B1. So F again is equal to M1 x1 double dot plus B1 x1 dot. And so we can rewrite this in terms of V, M1 V1 dot plus B1 V1. So now if we push with this force, first of all inertia pushes back, and then second of all this damper is going to push back. So let's go into the twilight zone again. Now we have a current source I. We have our mass M1 V1 dot, so that's the capacitance. But again, now we're looking at how do we dissipate energy based just on the velocity, or just on the voltage. And we actually know how to do that with a resistor. So B1 V1, but we can't just choose B1 as the value of the resistor, because voltage is a current times a resistance. And therefore the current is equal to 1 over the resistance times the voltage. So if our resistance is 1 over R, but the value in front of V1 is B1, then our resistor's value must be 1 over B1. So even though the spring acts like an inductor, we have to invert it to get the inductor's constant. And even though the dashpot, or the damper, acts like a resistor, we have to invert its value to get its resistance. So this is how we come up with, fundamentally from its atomic pieces, how a circuit would be analogous to a physical system. So let's look at an example from the text. This is an example where you can find this diagram and its analogous circuit. So here we have a mass M1. We're pulling on it with some force R of t. And then M1 is connected to 2 dashpots, and one of those dashpots has a mass and another spring in series with it. So we indicate velocity in this direction. And we remember that the sum of all forces is mass times acceleration. So M1 V1 dot, that's the direction downward, right? So we expect that R, which is our force, will be positive on the right-hand side. But then we're going to have negative values that are preventing us from doing that based on these 2 dashpots. So B2 V1 is going to be pointing in the opposite direction, it's negative. And B1 times V1 minus V2 is also negative, so it's pointing upward. Our second equation, based just on M2, means that we take just the dashpot times V1 minus V2, and then we subtract away the value of the spring. So as V2 moves down, we're expecting that we're going to get a force pulling up. So that's why that value is negative, whereas the B1 value is positive, because we wrote V1 minus V2 instead of V2 minus V1. If this doesn't make sense to you, you can go back and look at the diagrams that we did just on dashpots and just on springs to show how these values can be decomposed. So now we can rewrite this in terms of x1 and x2, obviously. And this is just a change of variables. So some have more dots and some have fewer dots now. But I'm staying with the v's for a reason that will become clear soon. So now I want to isolate the force and put it all on one side of the equation. So once you do that, you can come up with this rewriting. So now we have some current equal to pieces on the right, and then we have the sum of a bunch of other forces being equal to 0. So now we're going to rewrite this so that we'll have it on this page. And I want to consider for just a second that we're actually treating V not as velocity, but as voltage. So we did this with the atomic examples. Now I want to do it with a slightly more complicated example to show how these pieces compose. And R is going to be our current. So V1 dot is dV1 dt, or M1 times V1 dot is going to be some kind of a capacitance, C dV dt. The integral of V2 dt is the same, or is analogous to 1 over L times V2 dt, which is some current, because we know that V is L di dt. So now, again, we see that the mass acts like a capacitance, and that the K is the inverse to an inductance. So if we have K times the integral V2 dt, which we see up there in equation 2, that's 1 over L integral V2 dt. So our inductor's value, that is, what's the value for our inductor, is 1 over K. Because 1 over K is K. So for just a regular resistance, B times the voltage is 1 over the resistance of the voltage. So this gives us the analogous of what our currents are equal to. So in this case, again, we have dashpots that act a little bit like resistances, but this damper is actually inverse to a resistance. So because you have a damper, it acts like a resistance, but the value of that resistor is the inverse value of the damper. That is, R1 is equal to 1 over B1. Okay, so let's rewrite these equations again so that we have them. And now let's draw our circuit. So R is going to be the sum of a bunch of different forces. And so if we use KCL, then the sum of all the currents has to be equal to 0. So if we draw R going into this node and the other currents going out of the node, then R will be on the left-hand side and the other currents will be on the right-hand side. So the first current that comes out, M1 V1 dot, well, we use the mass M1 and we label that this node is V1 because the current through a capacitor is C dV dt. So here the value for C is M1 and the value for V is V1. So we have to decompose just a little bit some of these other pieces to find out that this second current is B2 times V1. And so in fact the value of the resistance is 1 over B2. We also have V1 minus V2 all multiplied by B1. So you can see in the equation 1 we have B1 plus B2 times V1, right? But when we translate that into the circuit, we're interested in the original resistor values. And so we're going to have one current attributed to the resistor B2, and we're going to have another current attributed to the resistance for B1. And so now we're actually going to make this resistor value 1 over B1 here, but we need to create another node V2 because we're interested in the potential V1 minus V2. So that second resistance here divides its current, and we'll see that in just a moment. So this current coming out of V2 will be divided in two ways. So one of the ways that the current in V2 is divided is that it goes through this capacitance M2. And then the other way that the current is divided is that we're interested in the current through the inductor. So K times the integral V2 dt. And remember that K here should be inverted. Let's fix that. So now we have our analogous circuit. And this analogous circuit may not look exactly like the diagram that we had before, but let's see if we can compare them. So here's the mechanical diagram. In the mechanical diagram we have some forces, we have some masses, we have some dashpots or dampers, and we have some springs. So in the circuit world, we first take the force, R. So R is divided among all of these objects. That is, when we pull down on M1, we divide its force between B1 and B2. One of these is supposed to be B1. I think it's, let me see if I can figure out which one it is. Yeah. So this value is supposed to be B1 here. So now, this force is divided and not shared. So we divide this between the dashpots B1 and B2. So to divide current, we do things in parallel. So we divide R by M1 times, or the capacitance M1, and we invert B2 to show that we divide the force through the resistor. And these forces F1 and F2 will map directly to the flow through resistor B1 and B2, or 1 over B1 and 1 over B2. But the resistor 1 over B2 is also dividing its force between mass M2 and K. And so it's got a share. So the same current that flows through B1, that is the same force up there, also has to be shared on the other side between two components. The mass M2, which shows up as a capacitance, and the spring K, which shows up as 1 over K, as an inductor. So this is your equivalent circuit. So I want to finish with something that I said at the beginning. The transform between physical system and electronic system is not for the faint of heart. You should not consider doing this just because you don't understand the physical system. Because if that's the case, you're going to find that if you try to do this on an examination, you may actually mess up the transformation between the physical system and the circuit. And so you're better at really spending time understanding why the physical system behaves like it does, rather than doing this transformation into the circuit and maybe not figuring out why it is that the circuit behaves this way. Why did I post this at all? Well, I know that some students were interested in understanding fundamentally why we can do the analogs in this way. So why would it make sense that the table, as it's written in the book, actually shows that a mass shows up as a capacitance and not the spring as a capacitance? And so I want to make sure that I advise you correctly. When you're working on homework assignments, if you want to do this to deepen your understanding of how these systems behave and what the physical phenomena that are underlying these systems is, that's fine. But if you're working on a high-stakes problem, like an exam problem, don't consider doing this. Instead, work on it straight from the direction in which it's given. So if I give you the physical system, work in the physical system domain. If I give the electric system, work in the electric system domain. If you want to consider making these analogs between mechanical and circuit, do it so that you can better understand how the physical system behaves, not so that you don't have to worry about understanding physical systems. Okay, so I know this is tricky. I know that it's tough to understand, and so please let me know if this video is helpful in any way.